Okay, thanks.
Okay, there we go. So now we're ready to go.
Mm-hmm. All right. So hi, everyone. Good morning, and welcome back to our workshop on model theory and combinatorics. Just a small announcement. So our second speaker today, Rihana Patel, had to cancel the talk due to some circumstances. So there will be only one talk today. And for this final talk of the workshop, I'm happy to welcome Martin Baes from Universitat Münster, who will tell us about Elekes-Szabó, weak general position, and generic nilprogressions.
Okay, thank you very much. So I'm going to talk about some joint work with Jan Dobrowolski and Tingxiang Zhou on Elekes-Szabó, and really trying to think about failure of general position in Elekes-Szabó, but concentrating in the end on nilprogressions in nilpotent algebraic groups. Okay, so my talk will have two parts. First, I'm going to talk really about Elekes-Szabó, and this will really be a matter of motivation for the second part of the talk. So my preliminaries, background, and motivation for the second part of the talk, which will be concentrating on groups. Okay, so let me go straight in. So I'm going to go straight to working non-standardly. So please do interrupt me during this first initial segment if anything's unclear, because otherwise things won't make sense later. So fix a non-principal ultrafilter U on natural numbers. And for a set A, an internal subset of the ultra power of A is just an element of the ultra power of the power set of A, or in other words, it's an ultra product of subsets of A. Okay, so an internal subset of A to the U is just an ultra product of xi, where each xi is a subset of A. And then one thing we can do with an internal set is to look at its cardinality. So you have a non-standard cardinality associated to internal set X, and that's just the ultra limit of the cardinalities of the coordinates xi. So interest in the case that these are almost always finite. So then this non-standard cardinality will be a non-standard natural number. In case we just call it infinity. So X will call internal set X pseudo-finite if it does have a non-standard finite cardinality. And then the key thing in this talk will be the Vygotsky-Wagner coarse pseudo-finite dimension of an internal set X. So for this, we have to pick some scaling. We'll call it a gauge, n. So this will always be some infinite non-standard natural number, capital N. And then with respect to such an n, the coarse pseudo-finite dimension of an internal set X is just the standard part of the logarithm base n of the cardinality of X. And we'll call this delta of X. Okay, so log n cardinality of X is some non-standard real, and then we take the actual real number closest to that, the standard part, if there is such a real, otherwise it's plus or minus infinity. Okay, and this works well. It behaves a lot like a dimension function. It's all very elementary, but for example, it satisfies that the dimension of the product is the sum of the dimensions, and the dimension of union is the max of the dimensions, and more such properties, which just follow from elementary counting. And one last little definition will say that an internal set X is broad if its pseudo-finite dimension is strictly between 0 and infinity. It's a positive real. So what does that mean more concretely? It means that the cardinality of X, the cardinality of X, is greater than some positive power of n and less than some positive power of n. Okay.
So this is just for internal sets, right?
Yeah. Yeah, X was always internal here. Yeah. Okay, no other questions on that? Good. Okay, so let me then really start by recalling the one-dimensional version of Elekes-Szabó. So if we have an algebraic surface V in C cubed, let's call it coherent if we have pseudo-finite sets x1, x2, and x3, each in non-standard complex numbers, such that setting our capital N, our gauge appropriately, we have that each of the xi has the same course pseudo-finite dimension 1, and the intersection of this variety with the product of the xi has dimension 2. So, for example, to make it clear what's going on, hopefully, if you consider the graph of addition, then that is coherent because we can take x1, x2, and x3 to all be an arithmetic progression of non-standard length n. So concretely, that's the ultra power of finite arithmetic progressions of lengths ni, where the ultra limit of the ni was n. Okay, and that will satisfy this because, well, the xi are all of the same size, all the same set. And if you look at the intersection with the graph of addition of the cube of this set, then you'll get about n squared points, because anything in minus n over 2 up to n over 2 plus something else and minus n over 2 up to n over 2 is in this interval. Yeah. And similarly for the multiplicative operation, the graph of that will also be coherent by thinking about geometric progressions, and similarly for the group operation of an elliptic curve, if you squeeze that into c cubed. And the other thing to say is that coherence is preserved under taking finite algebraic correspondences in the coordinates one at a time. So for example, if I, rather than looking at x, I look at x squared, and rather than y, I look at y cubed and replace z with z to the 5, then this will also be coherent because we can take the images of the arithmetic progression under the corresponding correspondences, taking powers here. Okay, and finally, before stating this Elekes-Szabó theorem in this case, let me make some, okay, I'm not very sure about this terminology, it's just for this talk. Let me define a ternary correspondence to be an algebraic surface in c cubed, such that when you take the projection to any pair of the coordinates, then that is dominant. So in other words, V is not lying above any curve in any pair of coordinates. Okay. Okay, and then we can state this Elekes-Szabó theorem in this case as saying that a ternary correspondence is coherent if and only if it's of this form that I just described. So it's in coordinate-wise finite-to-finite correspondence with the graph of addition in a one-dimensional algebraic group. Okay, and let me give a nice application of that, also due to Elekes-Szabó. So it's the orchard problem. So the problem is to find large finite subsets of the plane, so the real plane, with many collinear triples. So, okay, there are various ways to make this precise, with various decisions on what we mean by many. But one way to make it precise is to say we want to find, so yeah, a subset X, non-standard subset of the real plane with delta 1, but such that we have delta 2 triples distinct collinear. So it's one easy way to do that, which is to take an arithmetic progression or generalized arithmetic progression on a plane cubic curve. So for example, it's maybe a nice way to think of it with an elliptic curve, and then take, well, actually what's drawn here is a finite subgroup, but you could take more generally an arithmetic progression. And then because the group operation on an elliptic curve is given by collinearity, this will give you coherence. Okay, and here's another version of multiplicative type, where you have a circle and a line at infinity that isn't drawn. So these parallel lines will all meet at a single point on the line at infinity. So that gives you another example with a cubic curve, which here is a line union, a conic. Yeah, okay, and then a consequence of the Elekes-Szabó theorem I stated earlier is this result of Elekes-Szabó, that there's no other way to do that of this flavor. So there's no other way to find a solution to this problem, the orchard problem in this setting, by taking points on an irreducible plane curve, unless it's a cubic. Okay. Yeah, so you can't find an irreducible plane curve of degree greater than 3, such that you have a solution to the orchard problem given by taking points on that curve. Okay, and the idea, of course, is that you get coherence here, and hence a group operation. And the only way you get a group operation by collinearity on an algebraic curve is when it's a cubic curve. Okay, but there's some more work to actually prove it properly, but that's the idea. Okay, and then I wanted to talk about the higher dimensional version of this, or some higher dimensional versions of this, of the Elekes-Szabó theorem I stated first. So I don't really want to go into the proof, but very briefly, you can see Elekes-Szabó as being a matter of showing that a certain geometry of algebraic closure associated to coherence is modular, and then non-triviality lets you get a group configuration and hence a group. So this idea does go through in higher dimension, but we still need to have exchange, we still need to have a geometry. So in the original case, that was fine because we're working on C or on the curve. So it really was minimal. You become algebraic as soon as you have some algebraic dependence. So there's no issue, but for higher dimensional versions, we need some extra condition. So here's one that works, coarse general position. So if X is a broad pseudo-finite subset of an irreducible algebraic variety V, we'll say it's in coarse general position, or CGP for short, in V, if whenever we take a proper subvariety W of V, the intersection of X with that proper subvariety is very small. It has delta 0. Okay, so smaller than any positive power of the size of X, in other words. Okay, and then if we adjust the notion of the coherence to take this into account by making this definition, yep.
We require delta of X to be positive?
Broad included that. Broad meant positive delta and delta. Yeah. Yeah, so it's really dropping. Delta of X in sec W is less than delta of X in particular. Okay. Okay, and now if we have three varieties, W1, W2, and W3, let's say a subvariety of the product is CGP coherent. If there are now CGP xi and wi, each of dimension 1, such that the pseudo-finite dimension of the intersection of x1 times x2 times x3 with v is 2. So that's exactly the same as the definition of coherence I had earlier, except there the wi were all c, and CGP then was immediate because you don't have any proper subvarieties of the complex line other than points, for which it's clear that you have delta 0 because it's finite. Okay, so this is a generalization to higher dimension of that notion of coherence. Okay, and as before, let's call the ternary correspondence if it projects dominantly and with generically finite fibers to any pair of the coordinates. So that's again making it look geometrically in very rough terms like a group operation, so that then we can state like this, the version of Elekes-Szabó in this setting. So this was basically Elekes-Szabó, but then in this precise formulation, myself and Manuel, that a ternary correspondence V in a product W1, W2, W3 is CGP coherent if and only if it's in coordinate-wise finite correspondence with the graph of addition in a commutative algebraic group. Okay, so now it's still a commutative algebraic group, now arbitrary dimension, to be the dimension of Wi. Yeah, so just bumping things up. So it's if and only if. So going backwards now is a bit more tricky than just taking an arithmetic progression because we need to get CGP. So you need to see that you can take generalized arithmetic progressions in arbitrary commutative algebraic groups, which are CGP, but you can. Okay. Okay, and now what I really want to talk about is what happens when you delete the CGP condition. So this is all a rather restrictive setup where we just get a commutative algebraic group in the end. And there should be more interesting things that we can talk about. So how I'd like to think about this kind of model theoretically is that we're dealing here with the minimal situation, and the CGP is forcing us into the minimal situation. and there should be something analogous to LF1 categorical, almost LF1 categorical, where we relax that. So
that's a very small question. So this will also impose a condition on the dimension of V. Am I right?
This forces, this ternary correspondence forces that the Wi all of the same dimension, and V has twice that dimension, if you think about it.
Okay. Thanks.
Yeah. So I want to think about what happens when you relax this CGP condition. So the first thing to say is that if you want to get any reasonable structural consequence, you can't go too far in relaxing it. So you might think it would be enough to say that Xi is visky dense in Wi as a replacement for the CGP condition, but that really is too weak. So let me quickly give an example demonstrating that's too weak to get interesting structural information out. So suppose we take W1, W2, W3 all to be a single variety, which just contains some commutative algebraic group as a subvariety. So say it contains a line. G could be one-dimensional maybe. And then take an arbitrary ternary correspondence in W cubed with just the condition that when you restrict to this group G, it is the graph of addition on that group. So V is barely constrained at all. It's just on G, it has to be the graph of addition. Beyond that, it could be whatever it wants. And then already this will be coherent with Xi being visky dense. So explicitly, you can do this by taking X1 and X2 to be the union of, firstly, an arithmetic progression in G of a pseudo-finite length n, and then also, and that won't be Zariski dense so far, so also some Zariski dense subset of W, but very small, very sparse, just log n size. Right, so we've got this arithmetic progression on our algebraic group, but then union of a very sparse set, which is still Zariski dense. That's possible because log n is still infinite. Then if you let X3 be, well, a set of Zs such that X, Y, Z is in V and X and Y are in this set, then that will still have delta 1 because, because when you take this arithmetic progression plus itself, that's still size n, and then between these two sets, you're going to be getting just n log n at worst. So it will still overall be of size about n as far as exponents are concerned. So delta 1, and this will be delta 2. Okay, so this is coherent, but it's not, V is not constrained at all, really, beyond having this group structure in there somewhere. So this is not a good enough condition, is what this is meant to show. So Zariski density is not enough. So I think this suggests the following definition, and the rest of the talk is going to be trying to convince you that it's a reasonable definition in a way, which is weak general position. So the problem here, in a way, was that when we took this X and intersected with this G, which was a proper subvariety of W, the size of the intersection was still, in terms of delta, full. It was n, and the whole thing is just n plus log n. So that's what we avoid with this weak general position definition. So a broad pseudo-finite subset X of no reducible algebraic variety V is a weak general position, WGP, in V, if for any proper subvariety W of V, delta goes down. Delta of X intersect W is strictly less than delta of X. So it doesn't concentrate too much on any proper subvariety, in other words. It's allowed to concentrate somewhat. It's not going down to 0 necessarily. It doesn't concentrate too much. Right. Okay, and then again, we have notion of WGP coherent, which is just the exact same definition as before, but now with WGP Xi. So then we can ask, what V are WGP coherent? And I cannot give you a full answer, but I can give you a couple of examples. So the first shows that we now go beyond just commutative algebraic groups to nilpotent algebraic groups. So for example, if we take the Heisenberg group of 3x3 matrices with one on the diagonal, then the graph of the group operation is WGP coherent, and that's witnessed by this nil progression, nil box here. So this is an approximate subgroup, and it will witness WGP coherence. It is WGP, as one can check. Yeah, so we found commutative algebraic groups non-potent. But it's not just a matter of groups anymore. It's not that simple anymore if we work with WGP coherence. So for example, you can have things like this. So it's in a way an additive group fibered with the additive group, but twisted in a way that varies as you go across. So just this operation A1 B1 times A2 B2 is A1 plus A2 plus B1 squared B2 squared. And I could have taken pretty much any polynomial here, but this will work, comma B1 plus B2. So the second coordinate is just addition, the first coordinate, it's just addition, but twisted by this, which depends on the b's. So this is not in coordinate-wise correspondence with the graph of the group operation, but it is nonetheless WGP coherent. So yeah, so you see things are definitely more complicated when you try to work with this notion. But as far as we know, there are no seriously different examples that we know of. So as far as we know, working hypothesis, I don't want to call it conjecture, that WGP coherence comes from iterated abelian groups. Something like is happening here. And nilpotent groups are also in a way iterated abelian groups. So it seems plausible. Let me very briefly, without really saying anything, mention a test case for this hypothesis, which I think is interesting and is proving to be quite difficult, but we're working on it, which is to look at bumping up the orchard problem example by one dimension. So rather than looking in the plane, look in 3 space, and rather than looking at an algebraic curve, look at an algebraic surface, and cubic surfaces are particularly relevant. And then again, ask if we can get many points, a large set of points on the surface such that we get many collinear triples in the sense of having coherence of the set of distinct collinear triples where the X, Y, and Z are on the surface with WGP. So for what surfaces is this WGP coherent? So we don't have answers, but there seems to be a non-trivial problem. And our expectation, and we haven't found reason to doubt it, is that the only way to do this is to have S being a union of three equally spaced planes, and you get an example with grids quite easily. Okay, but now let me go, well, any questions before I go further? Okay, then let me go to the second part. That was all really just motivation for what's to come, which is considering the case of really the graph of a group operation. So this is maybe
sorry, Martin.
Yes.
In the matrix problem, what were the xi's?
This.
This is the xi's?
Yeah. So it's an approximate subgroup. So it will be
right.
A witness to coherence. Okay. That will maybe be even clearer when I get further on in the second section. There'll be more things like that. Okay, so we can ask for which connected algebraic groups G is the graph of the group operation WGP coherent. So that example above was showing that for the Heisenberg group, we do have WGP coherence. Yeah, we can ask what groups appear. So in other words, when do we have weak general position subsets of G, x1, x2, x3, each of delta 1 for an appropriate choice of gauge, such that when we look at the triples, x1, x2, x3 in x1 times x2, x times x3, such that x1 product with x2 equals x3 is delta 2. Many such triples. Okay, so that's a question, kind of specializing the general question in this case of just looking at the graph of the group operation. So if we replace WGP with CGP, then the Elekes-Szabó results I was talking about earlier are enough to answer this question and say that the answer is if and only if G is abelian, if and only if G is a commutative algebraic group, then it's CGP coherent. And only those are CGP coherent. So we want to do the same for WGP, and okay, here's the answer. This is then our main result here, is that the graph of multiplication in a connected algebraic group G is WGP coherent if and only if G is nilpotent. So we just go from commutative to nilpotent. So for those who know some of the VGT work, this may not be a particularly surprising statement, and really the forward direction going from WGP coherence of the graph of multiplication to the group being nilpotent is, well, it's very similar to work of Green and Tao on approximate subgroups of linear algebraic groups and characteristic 0, which are controlled by nilpotent approximate subgroups. And so we use ideas from that proof to prove the forward direction. In a way, there's not that much new going on in that direction, but we take the opportunity to present things in a nice pseudo-finite way. But the converse is actually, you might think it's the easy direction, saying that from a nilpotent algebraic group you find WGP coherent. You get WGP coherence of the graph of group operation. That was actually where the real work came in a way. So that's what I'll get to soon, hopefully.
Question at the second. Yep. Ask one question. So does your theorem one suggest the generalization of Elekes-Szabó for weakly?
That's the idea. Yes.
Yeah, WGP coherent. Yes.
Yes, that's the idea. But as I say, it's not simply a matter of saying that it's in coordinate-wise correspondence with the graph of a nilpotent algebraic group, because here's a counterexample.
Oh, I see.
So it's not that simple. So, okay, that's why I have this, this working hypothesis that it's something about fibering abelian algebraic groups, some iterated fibration, some analysis, something along those lines, but it's not clear exactly what the statement should be yet. Okay, but let me discuss the proof of this result now, is what the rest of the talk will be, proof of theorem 1. So the first thing is that in this case that we're working in a group, this WGP coherence reduces to thinking about WGP approximate subgroups. So that's via this result of Elekes-Szabó, Gauss, and Tao. So let me briefly explain that. So the idea is if we have coherence in our group, then that means we have large energy, as it's called, which just means that if we count how many 4 tuples, x1, x2, x1 prime, x2 prime, we have with xi being in capital Xi, such that x1 times x2 is equal to x1 prime times x2 prime, right? So this is seeing how many coincidences we get when we take products like this. Then this is large. So, and you can think of coherence as basically being non-expansion somewhere, and then that gives you this large energy. It's just straightforward calculation. Okay, and then the point is that there's this theorem of Tao, extending Alexander Gauss, which tells us that when we have large energy, it comes from an approximate subgroup. So we get an approximate subgroup, which is connected to, say, x1 in the sense that some translator of the approximate subgroup has large intersection with x1. Okay, so this is just a result that we use. So what that gives us in our pseudo-finite terms is that we have a coarse approximate subgroup. So to find out, so an internal subset X of G will be called a coarse approximate subgroup if firstly it's broad, so that meant positive delta, finite delta, it's symmetric and contains the identity. And when we look at x times x, it's contained in k times x for some internal k, with delta of k being 0. Okay, so if you like, it's a k approximate subgroup with k being of delta 0. So you define it. Yeah. Okay, then the point of this, of using this BSGT, Alexander Tau, is that it reduces our question about WGP coherent group operations to just asking which connected algebraic groups G admit a WGP coarse approximate subgroup. Okay. So we kind of symmetrified the problem and turned it into really thinking about approximate subgroups. Okay, so this is now what we will answer. So the answer again will be if and only if G is nilpotent. Okay. And I have lied slightly, but I won't tell you how I've lied. It's not important. Okay, so let me very briefly, because as I say, it's really just relying on other results, show you the forward direction that if you have a WGP coarse approximate subgroup in a connected algebraic group, then the group must be nilpotent. So, okay, so suppose X is a WGP coarse approximate subgroup of G. First trick to make things nice is to replace X with an actual subgroup, so a type internal subgroup. So type internal, I just mean, let's say, countable intersection of internal. Okay. So you get an actual type internal subgroup H of G, which contains X and has the same delta as X. Okay, and this is not deep. This is not stabilizer theorem. This is just a trick due to Hashofsky. So here's explicitly what you do. You just take H to be an intersection of appropriate pseudo-finite powers of X. Okay, now a part of the BGT work I mentioned earlier, or a recasting of it by Hashofsky, shows that a simple complex linear algebraic group has no broad type internal Zariski dense subgroup. Okay, keyword here was simple. So in simple, you do not have broad type internal Zariski dense subgroups. So that's okay. The BGT plus Hashofsky tells you such a thing would be actually internal, and then Jourdain tells you that that's not possible, because it would be essentially abelian, and it wouldn't be Zariski dense in this simple group. Okay, and then thinking about quotienting by the radical, we get down to semi-simple, and then by this, that can't happen. So it must be that G itself is solvable. Okay. And then if G is not nilpotent, so it's solvable non-nilpotent, then you get a field. So there's a nice argument of Pierre Green, which cooks out explicitly then a field. So you really get, in these terms, you get a broad type internal subfield of non-standard complex numbers. And such a thing cannot exist by some product. Again, because it would be actually internal, and we're in characteristic 0, and you don't have pseudo-finite fields in characteristic 0. Okay, so where did the WGP hypothesis, where was that used in this sketchy proof? Well, actually in two places. It was used here when quotienting out by the radical, and also here when getting this type internal subfield to see that you get broadness. So the point is that if you take the quotient of a WGP group, a group quotient, then the image will also be broad, because the fibers are then intersections with cosets of algebraic subgroups, proper algebraic subgroups. So they have bounded size in terms of delta because it's WGP. And so the quotient will still be broad. Yeah. Okay, that was sketchy, but hopefully gives you an idea. Okay, and now I want to spend the rest of the time talking about the converse. So it remains to show that any nilpotent complex algebraic group admits a WGP coarse approximate subgroup. Okay, so we will find such a thing as a pseudo-finite nil progression. So let me first tell you what a nil progression is. So just a finite one. So given some elements A1 up to AR of a group and some natural number M of the length, the nil progression generated by these elements A, nil progression of length M, is just the set of all words in these generators and their inverses, where for each I, we allow at most M instances of AI or AI inverse. I mean, you add up how many AIs you have and how many AI inverses you have, that should be at most M. Okay, and then the point is that if H is nilpotent, then the size of this will be polynomial in the length. It's polynomial growth. And then such a nil progression will be an approximate subgroup for some constant, depending only on the nilpotency class of H and the number of generators. Okay, so we're going to use that, but now take pseudo-finite length. So now fix G, a non-trivial connected nilpotent complex algebraic group. We want to find a WGP coarse approximate subgroup. So here's how we do it. Given some natural number R, set P sub R to be the nil progression on generators A of pseudo-finite length N, where A is an algebraically generic tuple of length R in our group. We can take it to be complex numbers. So in other words, no relations over the field definition of G. So transcendent degree of A over C0, where G is defined over C0, is R times dimension of G. Yeah, and then we just take an ultra product of finite nil progressions in A, given by the coordinates of lengths given by the coordinates of N. Okay, and then the point is, well, this is a coarse approximate subgroup, as follows from this fact about the finite version and G being nilpotent. So it remains to show that we can take it such that it's WGP in G. And we will see that that holds if we take R, the number of generators, large enough, but still finite. Okay, so then this is then the main thing to see. This is WGP, as the delta goes down when you intersect the proper subvariety, when R is large enough. Okay, very briefly, I'll really go through this remark, but you might think you could do better by taking R to be pseudo-finite infinite rather than a finite number. But that doesn't work when you get to properly nilpotent groups. You end up getting too large intersection with the center, for example. Okay, so we have to take finitely many generators like this. Okay, so there are really two parts to proving this lemma 1. One is when G is commutative, and the other is reducing to that in the case that G is nilpotent. So let me talk about that second part first. So reducing to the case of G being commutative. So suppose this lemma holds when G is commutative, and I'll indicate how to deduce it for G nilpotent, quite sketchily. So first, let me discuss the case that G is nilpotent of class 2. So then, okay, so the first trick is to, instead of working directly with G in this nil progression, look upstairs in the algebra and at a nil box like this. So, okay, so now, yeah, define BR to be this. So it's a this box with pseudo-finite side length with generators BI, where BI is a lift of AI into X. And then also we have just added on a box of side length n squared with generators the Lie brackets of bi and bj, I and j varying. So yeah, first point is that this nil box is just as good as the nil progression. So you have mutual control between the image of the nil box and the nil progression. So roughly the idea, I think it's maybe nice to think of it like this. So in the nil progression, we're allowed so many A1, say, and so many A2, but we can put them in either order. And then if you commute these n A1s past these n A2s, then because we're nilpotent class 2, so the commutator is central, we get out n squared copies of the commutator, right? So this is why you have this n squared here. Okay, so now the idea is to consider quotienting out by the derived subgroup, commutator subgroup, or the same thing in Lie algebra. So if we look at the image of this nil box under quotienting by the commutator subgroup, then you get just this left part. The image there's this left part. This part dies, and if you intersect with the commutator subgroup, then you just get this right part. So it splits up into these two parts nicely. So now if we take W, a proper subvariety of our group G, then we can correspondingly consider quotienting by the derived subgroup. So either the image of W under that quotient map will be proper, or the fibers, the intersections with cosets of G prime, will generically be proper subsets of these cosets, right? So in either case, we are dealing with an abelian group then. So G prime is abelian and G mod G prime is abelian because we're nilpotency class 2. And then the abelian case, which I said we should assume for now, will tell us that we do get appropriate bounds. So using that, we're looking at these arithmetic progressions, generalized arithmetic progressions in these abelian groups. Okay, skipping over lots of details, but hopefully it gives you an idea. And then because it's just because it's split up like this, you just add the bounds and you get a proper bound. So you get WGP. Okay, so quickly, what happens more generally for arbitrary nilpotency class? Well, idea is to quotient out by the abelian term at the end of the descending central series to get something of the low nilpotency class to which we can apply induction. So it's basically the same idea, but we have some complications. So you get nil boxes of the same form in n to the m in commutators of length m, but you have this annoying phenomenon that in some the algebras you can have short luminomials which are already in Gn, ones of length less than n which already land in Gn. So you have to think about earlier terms when you intersect Gn. And the monomials themselves might not have generic image in Gn, so you have to apply some Hilbert decomposability and consider sums of them, and make sure your R that you choose is large enough that you get enough independent generics. Okay, skipping past stuff, but morally it's not too difficult, but there are details. Okay, but now I want to talk about the commutative case in the remaining time. So this turns out already to be interesting. So, well, the first case is that you're dealing just with a vector group, power of the additive group, and that's not interesting at all. It's just very easy. So if you're in GA to the D, and you look at minus n up to n to the D, then that's already WGP, because if you intersect with a subvariety, consider projecting in some direction so you get finite fibers, then you'll see that you get by some induction, you get a good bound like this. Okay, so not much to say about the additive case, but for the semi-abelian case, there's already something to say. So it's a matter of mod LN. So, okay. So if G is semi-abelian, gamma, a finitely generated subgroup, well, we want to consider gamma being generated by our independent generics and see that we get small intersections with subvarieties W. So you can do this using model lang, and I think you basically have to. So if gamma is a finitely generated subgroup, statement of model lang, if gamma is a finitely generated subgroup of semi-abelian variety G, and W is an irreducible subvariety, then W intersect gamma, sorry, if W intersect gamma is viscally dense in W, then W must be a coset of an algebraic subgroup. That's this theorem. So we can apply this in the case of gamma being generic, being generated by a generic tuple like this. So then if you take any element, any non-trivial element of this group, it will be a generic element of G. So it won't be in any proper algebraic subgroup of G, because they're all defined over the field definition of G, or its algebraic closure. So if we apply this, if we take W contained in G, an infinite subvariety in which W intersect gamma is viscally dense, then it must be a coset of an algebraic subgroup, but it must contain at least 2 points of gamma if W is infinite. So the difference of them will be in this subgroup. So that subgroup can't be a proper algebraic subgroup. So W must be the whole of G. That's what you get from model lang and genericity. So if W is a proper subvariety of G and gamma intersect W is infinite, then looking at the viscally closure of that infinite set will get you a contradiction to this. So it must be finite. Okay, and moreover, this happens uniformly. So we get that if you take this, this generalized arithmetic progression generated by A, then it's in Wgp in a very strong way, because you get uniformly finite intersections with proper subvarieties. Yeah, okay. And now we want to consider arbitrary commutative algebraic groups. So you might think it's just a matter of putting together these two things, but it's not really quite that simple. So yeah, any commutative algebraic group is a combination of semi-abelian and additive, but not in a trivial way, not in a split way. So, so we had to prove a version of model lang for this. So a pretty weak one. Okay, I'm almost out of time, but let me say very quickly. So if you have a connected commutative algebraic group G, you can write it as G0 direct sum V0, where V0 is a vector group, and G0 is the Zariski closure of the torsion of G, which is what's called almost semi-abelian. So for example, the universal vectorial extension of an abelian variety will be something you can get here, almost semi-abelian. Okay, and then we found this version of generic model lang for an arbitrary group, arbitrary commutative algebraic group G. So it looks like this: if W contained in G is an infinite irreducible subvariety, and W intersect gamma is viscally dense in W, then W must be G0, the whole of G0, plus some arbitrary irreducible subvariety of the vector group. So we're reducing to the vector group and getting something like we had in the semi-abelian case on the almost semi-abelian part. Yeah. So in particular, if G is almost semi-abelian, we just get W equals G0 here. And if it's a vector group, we get nothing at all. W is W. And moreover, this holds uniformly. Okay, so then in the same way that it was enough in the semi-abelian case, that is enough when you combine with the GA to the N case to handle the vector group to show that this generic arithmetic progression is Wgp for R large enough, at least as large as the dimension of the vectorial part. And that's enough to prove theorem 1 using the reduction from nilpotent to abelian, which I explained. Okay, and I'm out of time, so I'll stop. It was a bit rushed, but okay.
All right. Yeah, let's thank, excuse me, let's thank the speaker for this very nice talk. And are there any questions or comments, either from the audience live or online?
The fact that gamma is a generic subgroup, right?
Can you say this again? Sorry, I didn't get it.
You use very much the fact that gamma is generated by a generic tuple.
right?
Yes, for this statement, yes. Sorry, yeah, but it'll be the whole of GNOT like this. So yeah, the general question of what model allowing should be for arbitrary commutative algebraic groups seems to be very open. I mean, okay, it's known that you can't get a really nice statement like in the semi-Abelian case, but there are some results in some specific settings, like when you just have one-dimensional additive part, there's a result. Yeah, but it seems to be an open problem in general, even without a clear idea of what the statement should be. But for the generic case, it's a lot easier. Yeah, and as I wrote here, but didn't get to, I mean, the idea is to use Michowski's proof, which only makes sense because we're dealing with generic points. You can use DCF tricks.
May I ask one question?
Yes.
So, I mean, why can't, because if we are already in a Abelian case, why can't we just conclude that there is a subset in the generic position, and as a consequence, it is already in the weak generic position? Because don't we have in a Abelian group case, don't we just have something that is in the strong generic position in general?
Not to my knowledge. I mean, okay, here you do in the semi-Abelian case. But not trivially.
I see.
Well, and
so,
okay, sorry, and in the additive case, you don't. Right. I don't think you can get it. Yeah, of course you can't. I mean, okay, well, okay, so in the additive case, you can always intersect with a line. If you take as long as you have, unless you have bounded length in your generalized arithmetic progression, you can just intersect with the line generated by a generator, right? That will be a subvariety. And then that will be infinite. Okay, you could consider the case where you have bounded length and unbounded number of generators.
So that means that there is no analog of your theorem 1 for generic position and Abelian group, right? So there's no current analog.
Yeah, we don't know. I know. Okay. Yeah, even in yeah, we don't know. We don't know. So yeah, actually, we left it as a question in my paper with Emmanuel, whether just in the additive group you can find, yeah, whether you can find fully general position approximate subgroups. Yeah, there's a question in there somewhere fairly near the end, which would be exactly that. But we didn't get anywhere with answering it. Asked some people.
Are there any further questions?
No, can I ask another question?
Yeah.
Yes,
So, so does your theorem 1 seems to suggest that we should strengthen this notion of weak generic position a little bit, so that, because here there's a counterexample.
Right. Strengthen it so that you do just get groups, but still allowing nilpotent groups. Yes, that will be interesting. I don't know of a way to do that. I would be surprised if it were. And okay, so there's another question, which is if you can weaken CGP, just a little, so not going all the way to WGP in such a way that you still get the same Elekes-Szabó result, still commutative algebraic groups. Okay, we also had a question like that in my paper, the manual. So yeah, that's a candidate for it. Last in pink, general position. Where you say the amount delta goes down should be proportional to the dimension of the variety you're intersecting with. And it seems plausible that then you still get the same result, but certainly you don't get non-abelian nilpotent groups in that case. Oh, sorry, with a slightly stronger condition you don't. Yeah, so yeah, it's unclear what other possibilities you have between these two, between CGP and WGP.
Thanks.
But I think this is a natural one myself. And yes, you get things which aren't just groups, but that makes it more interesting. Yeah.
All right.
Yes.
Can I ask one more question? Yeah. So the algebraicity of the group is heavily used. Is there any chance to get rid of some of it, or
Ooh.
or to replace it by, I don't know, Lie groups or minimal groups?
Yeah, I see. That sounds like a nice question. But yeah, I mean, well, for this direction, it's very much relying on
Right.
And for the other direction, well, it's just that. Well, as soon as you get into linear. Yeah, sorry, what am I saying? Right. Yeah, I don't know. That's a good question. I haven't thought about it. Yeah.
Thanks.
Okay. Are there any further questions? Last question, maybe. If not, let's thank Martin again.